SwayamPrabha. Digital India. Educated India.
Okay, greetings. Welcome to this course on control systems. So, this is a course on control systems, and to be more specific, this is a first level undergraduate course on control systems, like where we are going to learn the basics behind what is called as classical control theory, and we would learn how to design controllers for dynamic systems that we encounter in practice. Okay. So, before we go into the details of what we would learn in this particular course, let us just look at the title of this course, right. So, there are two words in this title. So, the first word is what we call as a system. So, let us discuss what we would refer to as a system in this particular course. So, for us a system is an entity to which we give an input u of t and we get an output y of t. Okay. So, this is typically called as a dynamic system in the sense that like it essentially deals with variables like inputs and outputs that are functions of time. Okay. So, as far as this dynamic system is concerned, like time is the independent variable, and all other variables that are associated with the system are functions of time. Okay. So, all variables that are associated with the system are functions of time. Okay. So, we are going to deal with the so called dynamic systems, like where essentially variables change with time, and a system or a process or a plant essentially is an entity that is given an input and produces an output. Okay. So, that is the visualization we would be having, right, for the system. So, once again like there are alternative terms for the system, like some would call this system as a plant. Okay. If you go to chemical engineering, for example, like this would be they would be dealing with processes, like so a process is also visualized as an entity to which we give an input and we get an output, right. So, there are various terms that are typically used. So, for us, like a system is a collection of objects. Okay. Let me group it as one phrase, or a process, okay, that is under study. Okay. So, for that is what we would refer to as a system. Okay. So, of course, although we are not going to repeatedly use various adjectives to denote the type of systems that we are going to look at, we will first study what class of systems that we are going to be concentrating on, and then we will go forward. Okay. So, the class of dynamic systems that we would be looking at in this particular course belong to what are called as linear time invariant causal dynamic systems, and by and large we will restrict ourselves to what are called single input single output systems. Okay. So before we get into that, you know, like we would see that mathematically we can visualize a system, a dynamic system, as a mapping S from u of t to y of t. Okay. So that is what we are going to say is that we would have y of t to be equal to s of u of t. Okay. So essentially we would picturize a system as a mapping S which takes an input ut and delivers an output y of t. Okay. So that is a mathematical visualization of a dynamic system. Okay. So given this, you know, like there are various classes of systems that one could essentially study. So let us look at some classes of dynamic systems. So as far as classification of dynamic systems is concerned, so the first classification that we would consider is based on the number of inputs and outputs. Okay. So what we abbreviate as SISO and MIMO. So what is SISO? SISO is nothing but single input, single output, and the abbreviation MIMO stands for multiple input, multiple output systems. Okay. So see, we can visualize in fact even the input and the output, right, function as a mapping from the time domain to the domain of real numbers, right. See, for example, if I deal with a single input single output system, right, I can say even the input u is a mapping from the field of real numbers to the field of real numbers, right, because t belongs to the field of real numbers, right. So essentially we take time and then like the input is a function of time, and in the case of a single input single output system, the input u is a scalar valued function of time. So u would be a scalar valued function of time, right. So that is why we are writing it in this form, and similarly the output y is also a scalar valued function of time. Okay. So that is essentially a single input single output system. On the other hand, let us say we have let us say m inputs and p outputs, okay, with m being greater than 1 and also p being greater than 1. What is going to happen is that we would have our input to be a vector valued function which will take time and then map it to a vector of dimension m. Similarly, I would have the output vector to be a vector valued function of time which will map it to a vector of dimension p. Okay. So that will be a scenario of multiple input multiple output system. Okay. So in this particular course we are going to be interested in SISO systems, okay, SISO dynamic systems. Okay. So that is the class of systems we would be focusing on in this particular course. Okay. So the first classification was based on the number of inputs and outputs. The second classification that we are going to look at is whether a particular system is linear or non-linear. So what do we mean by this, right? So let us look at the definition of linearity shortly, right. So, let us say we have a system, yes, and let us say we provide an input u1 of t and we get an output y1 of t, and to the same system, and let us say we provide an input u2 of t and we get an output y2 of t. Now, given these two arbitrary input output combinations, right, the question that we ask ourselves is that if to the system we provide an input that is the sum of these two arbitrary inputs u1 plus u2, and if the output is also the sum of the two individual outputs y1 and y2 corresponding to u1 and u2, and if I give any input which is an arbitrary scalar multiple of, let us say, any arbitrary input u1, and if the output is the same scalar multiple of the corresponding output y1, right, corresponding to u1, then the system is said to be a linear one, okay, provided these two conditions are satisfied. So, condition 1, condition 2. Okay. So, the first condition what is typically referred to as additivity, the second condition is referred to as homogeneity, right. So, the same definition, so this is the definition of a linear system. The same definition can be rewritten in this way. So, let us say if I have a system S, the same system S, let us say I provide an input which is a linear, any arbitrary linear combination of u1 and u2. That means that I am providing a input like C1 u1t plus C2 u2t, where C1 and C2 are two real numbers. The question is whether I get the same linear combination of the two corresponding outputs y1 and y2, right. So, if this holds true, then the system is linear. Okay. So, there are two alternative what to say ways of defining, equivalent ways of defining a linear system. One is this, okay, and the second one is this. Okay. So, typically people call this as the principle of superposition, right, for linear mappings. So, that is what it is called as. So, essentially a linear system, you know, like satisfies, you know, like these conditions, right. So, of course, we would see that in reality, you know, like most processes, most plans, most systems are going to be non-linear, right. So, linearity by and large we would realize if we, when we work with practical problems, is that it is going to be an approximation of reality that should be kept in mind. Okay. So, in this particular course, you know, like we are going to deal with linear systems. Okay. So, we'll after we go through all the classifications, we will summarize what we are going to deal with, right. So, finally, so the third classification that we are going to look at is that of a time invariant system versus a time varying system. Okay. So, the question is that, like, what is this concept of time invariance? So, what is time invariance? Let me demonstrate by a simple diagram. So, let us say I have a system and I provide some input to it, okay, u of t. Okay, at time t equals 0, let us say I provide a step input and I get an output which is some output like this. Okay. Now, let us say I now provide the same input u of t after a time interval of, let us say, capital T, I provide the same input u of t, but I essentially provide it after a time interval of capital T. The question becomes, like do I get the same output? If the output is the same function which is delayed by capital T, then the system is said to be time invariance, right. So, or in other words, the question that we are asking ourselves is that, like, do we get the same output if we provide the same input no matter at what time do we provide the input to the system, okay. If that is the case, then the system is said to be time invariant, okay. So, let me write it down. So, a time invariant system is one where a time invariant system is one that provides the same output for the same input irrespective of when the input is given. So, what is an example? Let us say like we take the example of a ceiling fan, right, that most of us encounter every day. So, suppose like if I come and switch on a ceiling fan, right. So, I am providing an electrical signal as an input to the system, right, and let us say the output of the system is the RPM of the fan, right. So, the speed of rotation of the fan. So, let us say I switch on the fan today and I give some electrical input to the fan, and let us say the speed of the fan is, let us say, 100 RPM, okay, and I come tomorrow and switch on the same fan, provided the input is the same, the electrical input is the same, right. So, I would expect the speed to be close to 100 RPM once again. Now, if I come after a month and switch on the same fan, there may be some wear and tear in the fan. So, given the same electrical input signal, like I may get the RPM as 99.5, right, for example. Let us say I come 1 year down the line and switch on the same fan with giving the same electrical input signal, the RPM may be 99 RPM, for example, right. So, one gets the idea, right, where we are headed. So, all systems like their characteristics or dynamic characteristics change with time, right, due to various factors. So, in the case of a fan, that may be some wear and tear, like the components might have become old, right. So, then the system's response changes. Now, the question that we are asking ourselves is that, like, in the time scale of interest, as far as a systems analysis is concerned, like does the response characteristics of the system or do the response characteristics of the system remain more or less the same? If that is the case, then we approximate the system as a time invariant system. So, in the case of a fan, let us say I want to analyze the fan only for a few minutes. So, in those few minutes I can reasonably assume that the response characteristics of the fan is not going to change. So, what do I mean by that? In a time scale of a few minutes, if I provide the same electrical signal at any instant of time, I am going to get close to 100 RPM, right. So, which is what I started off with, right. On the other hand, if I use a fan in an industrial application where it is supposed to run for months without any shutdown, then I need to be a bit more careful, right. Then my time scale of interest goes in the order of months. So, then we need to ask ourselves the question, like do I need to consider the variation in the system's response characteristics and model the system as a time varying system? So, that is a question which should be asked then, okay. So, in our course, like we would work with what are called time invariant systems, okay. So, that is the scope of our particular course. So, so as far as we are concerned, so what is the mathematical definition of time invariant systems? If y of t is s of u of t, then time invariance implies that y of t minus tau or s of u of t minus tau is going to be equal to y of t minus capital T, right, sorry, for all capital T belonging to the field of real numbers. Okay, so in a sense, like if I shift the input by a time of capital T, I should get the same output shifted by the same amount of time, right. So that is what time invariance means. Okay, so in this particular course we are going to work with time invariant systems. Okay, once again, like time invariance is an approximation, right. I am sure all of us agree that if you look at processes and systems that surround us, you would see that no system provides the same output like at any point of time in its entire lifetime, right. So, so time variance may become important, right. So, but the question we need to ask ourselves is that, like, what is the time scale of interest vis-a-vis the time scale over which the system's characteristics change, right. So, that is the question we need to ask ourselves, right, when we decide to approximate something as time invariant or time varying. So, another classification that we are going to do is that of causal systems versus non-causal systems. So, what is a causal system? A causal system is one where the output at any instant of time depends only on past and current inputs. So, a causal system is one in effect which that is non-anticipative. Okay, it does not essentially try to what to say, figure out like what inputs may come to the system in the near future and take action right now. Okay, so a causal system is non-anticipative. Okay, that is very, very important. Okay, whereas a non-causal system is anticipative, right. Okay. So, that is the difference between causal and non-causal, and in this particular course we are going to consider systems that are causal. Okay. So, if we look at this particular course, okay, so if you recall where we really started off, right. So, and essentially what we are doing in this particular course, 1 minute, So, yeah. So, what we are essentially doing, we started off with the title of this course, right. That is what we have done. So, I am just touching upon the two words in this title, right. So, the first word we started off looking at is the word systems, right. So, if we look at it, we are going to look at what are called dynamic systems. Okay, I am going to write summarize all the adjectives that we have encountered. We are going to look at causal systems. Okay, we are going to look at time invariant systems. Okay, we are going to look at linear systems. Okay, and we are going to look at single input, single output systems. Okay. So, this is the class of systems that will be under study, okay, in this course. Okay. So, we are going to consider SISO, linear time invariant, causal, dynamic systems. Okay. I hope through this discussion it is clear as to what each one of these words mean, right. So, by and large linear time invariant is abbreviated as LTI. Okay, the abbreviation LTI stands for linear time invariant. Typically LTV stands for linear time varying systems. Okay. So, this is the class of systems that we are going to study. Of course, when I ask the question, hey, is this a reasonable class of systems to study? And the answer is yes. This is a useful class of systems to study. Okay, like because we will see that, you know, like when we later in this particular course, when we look at case studies and so on, this is a reasonable approximation, right. So, as far as many practical problems are concerned. Okay. So, this is a useful class of systems to consider and study. Okay. So, that is what we are going to do in this particular, that is what we are going to study in this particular course, right, this class of systems. Okay. Now, having looked at the word system, now we come to the word control. Okay. So, let us say, you know, like what is control? You know, like the word control essentially, as far as this particular course is concerned, you know, we look at the word control to mean making a system. Of course, from here onwards, you know, like we are going to consider this class of system, you know, like that is what we are going to be interested in. In general, control is making a system behave as designed. Okay. So, that in a very generic sense is what we would refer to as control. Okay. Now, the questions are like how do we regulate the system, right. So, that is something which we are going to look at, right. So, let us look at an example, right. So, let us say I consider for example a DC motor, okay, just to consider this. Okay. So, let us say, you know, like the input to the DC motor, let us say I am doing armature control. So, let us say I provide an voltage V of t to the DC motor, and let us say the shaft speed, okay, omega t is the output of the DC motor. Okay. So, essentially I visualize the DC motor as a system to which I provide an voltage input V of t and get the speed output, right, omega of t. Now, the question that we ask ourselves when we want to design controller is that suppose if I want to essentially maintain the speed of the DC motor's output shaft at a particular value, right, what voltage input do I need to provide. Okay. So, that is the question we ask when we want to control this DC motor. Okay. So, what is the question that we are going to ask? Okay. If we wish to achieve a omega desired, okay, there is a desired angular speed for the DC motor, what is the input voltage that should be provided. Okay. So, that is the question we ask ourselves when we want to control the system. Okay. So, this whole course is about okay, learning how do we do this process. Okay. Like, so that is the idea behind this entire course, right. So, so in a general sense, you know, like what we will do is that we are going to learn how to design controllers, you know, like for many practical systems that belong to this class, right, or that can be approximated by this class of systems, and essentially get a output which I desire, right, from that particular system. Okay. So, that is what we are going to do. And what is our approach that we are going to follow? So, in a very generic sense, you know, like what we are going to follow is that we are first going to develop a mathematical representation for S. Okay, that is the first step. Okay, so if you recall what was S, S was the mapping between the input and the output. The process that we will follow is essentially get a mapping for S. So this typically constitutes what is called as mathematical modeling, right, for the dynamic systems. So this comes through mathematical modeling of dynamic systems. Okay. So of course there can be various ways of obtaining these mathematical models, you know, like so by and large in this particular course we would employ physics based models. Of course one can also have data driven models or empirical models, and sometimes, you know, we use both, right. So we use physics to essentially derive part of the model, and a part of the model is obtained by using experimental data, right. So that can be a semi empirical approach also. Okay. So but we first step is to essentially develop a mathematical representation for the what to say, mapping S, and then like second step is to analyze the system response. Okay. And then the third step is essentially to design the controller. Okay. So in a very broad sense, right, a big picture view perspective, these are the three steps involved in our approach, okay, which we are going to learn in this particular course. So essentially the first step is essentially to get a mathematical representation for this mapping S, okay, which is obtained by and large through this mathematical modeling of dynamic systems, right. And as I mentioned, you know, like we can have you know, like let us say physics based modeling, okay, where we use laws of physics to essentially model the system. We can have data driven or an empirical approach, okay. Sometimes we can have a mix of both, okay. So to essentially model the dynamic systems. Of course there are various categories of models. We will also see, you know, like which class of models we are going to look at, okay.